Our next speaker is Professor Shun-Qing from Hong Kong University. He will talk about impurity-induced bound states in topological insulators and superconductors. Thank you.
Thank you. I'm from the University of Hong Kong. This university is not this one. It's a university at Hong Kong Island. That's a unique university at Hong Kong Island. Today, I talk about the impurity-induced bound state in the topological insulator or superconductors. We talk a lot about the surface state related to in the topological insulator. Actually, if the system has impurity or defect, it's very easy to induce the bound state. This bound state is an in-gap bound state. So actually, we have talked a lot about the topological insulators. I make a summarize about the family members of topological insulators and the superconductors. So we have two lines. One is from the Hall effector to the quantum Hall effectors, and then to the quantum anomalous Hall effectors to the quantum spin Hall effectors. Then this quantum spin Hall effect generalized to the three-dimensional case. If you reduce the dimensionalities, actually it's the one-dimensional topological insulator. Actually, these materials, I think, has been discovered long ago, but no one realized this actually is one-dimensional topological insulators. So I think the more physics is contained in the helium threes, the A phase and the B phase. So if you check the fundamentals equations, you will find from this the system actually has covered all the properties in this one. So I think this is another line. Of course, so this is a spin triplet superconductors. So someone claims that has already observed the age state, but I think it maybe need more experiment to check. Okay, this is now to describe this the systems that cut a lot of the materials. So if you want to consider an insulator, so we need to start from the multiples, the band, the structures. I think the simplest case is the Dirac equations, which described, for example, the four band, the problems. That's for the elementary particles with spin 1/2. So from these equations, so if you change the sign of the mass, so we have so-called band inversions. So, but however, the band inversions is not enough to give the band topology. So the reason is very simple. If you change the sign of the mass, then you can also change the sign of the betas. And all these edge break relations are satisfied. So the topology for the positive sign, the mass, and the negative mass are the same in these equations. So now we know actually these equations is a marginal between topological trivials and non-trivials. Now we can make a revision. We just introduce additional terms, the quadratic terms proportional to the momentums. So if you keep this alpha and beta, this Dirac matrix, I think this is very easy to solve. So some mathematician says this is not real the Dirac equation since we introduced this quadratic the corrections. But I have no better name for these equations. So we say this is a modified Dirac equations. So why this equations is completely different from the original Dirac equation? So you can see the spin distributions in the momentum space. If you take the periodic boundary conditions and the momentum is good quantum numbers, so and you just plot along the x directions, If the p equal to 0, so the sign of the m define the spin orientations in the ground state, right? So if you increase the p along, say, along the x directions, then this linear term will be the dominated. If you continue to increase the momentums, you'll find these terms will determine the spin orientations in the ground state. So we have two different cases. One is M and B has a different signs. So in this case, you see at the p equal to 0 and at the p for very large, the spins are partners. But in this case, you see these spins will be flipped from at this 2 point. This actually is determining the different topology in these equations. So one is so-called topologically the trivial, another is non-trivials. So we can calculate, for example, some of the topological invariant. For example, in 2 dimensions, we can calculate the Z2 index. So it has the conditions. In 1 dimensions, we can calculate the so-called the Whiting numbers and so on. So, but the pictures, I think, is consistent with these two. So now, after we have an equation for this box state, so we would like to check what happens in these equations. So this equation actually can apply to a lot of the system. For example, the one-dimensional so-called SSH models for the polymer, and the PV, the superconductors introduced by the KTF models, and the 2 dimensions, even the 3 dimensions. You find we can use these simple equations to describe all the properties. So if you solve this equation, because this equation is simple, we can solve it exactly with some of the boundaries. So in 1 dimensions, we can find the so-called the end state. In 1 dimensions, the boundary is the end. We can find the end state with a 0 energy mode. And in the 2 dimensions, we have the chiral edge states. And the 3 dimensions, we can give a so-called Dirac cones for the surface states. So here also, I think this equation is very important in my theory. I think it seems a lot of the problem can be reduced to these ones. So this is a 1 dimension, and this is a 4x4. In some cases, we can reduce it by a 2x2 matrix. This is a decoupled. So we first solve these equations, and then we generalize to the higher dimensions. So I give solutions. I think this is a very good exercise for the course of quantum mechanics. So this is ordinary differential equations, right? We can first use the operator to replace this the momentums. If we have the boundaries, we need to use this the operators. We can set the trial wave functions and introduce the boundary conditions. Since we want to find some the bound state near the boundaries, so we take the wave function should be vanished at very far away, and also vanish it at the end of the system. So in this case, we can solve it. The final solutions is simple. We have 2 solutions. Depends on the signs of the M and B. If MB greater than 0s, we have solutions for the 0 energy mode. If the MB less than 0, this solution disappears. So this is consistent with what I claimed, the conditions for the topologically trivial and non-trivials. So the size, actually the size of the end state is determined by these 2 parameters. So when these are near the so-called transition point, if the gap is very, very small, so actually the size of this bound state is determined by these 2 parameters. So mv is momentums, h divided mv is the length. Another one, b, has dimensions of 1 of m's. So these 2 lengths determine the size of if the m approach to 0s, so this state will disappear. So topological quantum phase transitions occurs. So if we consider the impurities in the 1 dimensions, So simplest case, we simply cut the one line, the dimensional the lines. So we have two ends. So then we have this two state if m and b less than zeros, right? But if you use a glue, connect these two ends, say we introduce something, the potentials, you'll find these two states will not disperse immediately. If this in one dimension, if the v is not equal to 0, we can always find the two bounded states between in the gap. So the picture is very clear. This is calculations for we solve this model from these models. So this is one dimensions. So for two dimensions, so you will see we just add take the pz equal to 0. We have a px and py. We take periodic boundary condition along the y direction, along the y directions, and then this 4x4 the matrix can be decoupled the 2x2 matrix. But this is a 2x2 matrix, right? And we should notice that the one has a positive sign, another has a negative sign. This the sign are different at these two equations. So you will still use this take the boundary conditions and the hills. So you see what happens. We can solve it exactly. I mean, this problem can be solved analytically. But we have a simple way to get some result from the solutions of one dimensions. So if you write this equation in two parts, this is py dependent. Since the py is a good quantum numbers, so we use this py as a C number and write this equation in two parts. So this equations is a one dimensions. So we can regard this part as a perturbations if the p is not very large, py is not very large. So then you can calculate the dispersion for the py. It is not equal to zeros. So you got the two dispersions. One is proportional to the py, another proportional to minus py. At p equal to 0, you see this disappear. So what's this? Actually, this one has a positive the velocity. Another one has a negative velocity. This is a Hurdiker's edge states. Hurdiker edge states. This is for the so-called quantum spin Hall effect. So if we have a single the defect is in two dimensions, so you can see what happens. So if this you can assume we just punch a hole in the two systems, right? Then with this hole has a large boundaries. So there is an edge state around the boundaries, a boundary. Then the energies should be proportional to the p, per p. If the radius becomes smaller and smaller, so this momentum, momentums will be discrete, become the discrete, right? This is proportional to the n integers. This 1/2 actually come from the spin. The total angular momentum in this problem is orbital angular momentum plus the spin. So we have a 1/2 here. Sometimes people also would like to say this comes from the so-called non-trivial Barry phase. When this R becomes smaller and smaller, a lot of state will be expelled from the band gap. This is just reduce the radius. But no matter how small of this radius, at least we have one pair of the state in the gap. So we call this in-gap bound state. So you see, it's very easy to form the in-gap bound state around the defectors. So if a system contains a lot of the defect, we always say, oh, surface state or edge state is very stable. It is protected by the time reversal symmetry. So if we introduce the defect, this defect doesn't break any symmetries. If you introduce that, each defect can induce the in-gap bound state surrounded. So if the concentration of the defect become larger and larger, this bound state can be the wave function of the bound state may have an overlap. Then the edge state from this side to this side can be connected. If these are connected, then we break this so-called the topological insulators. And this is two different the geometry. One is use periodical boundary conditions. We have a low the edge state. Other one has a open boundary condition. We have edge states. So then you see we can show do these calculations in a torus. To show the formation of impurity band. If this has the lattice is 20 cross the 72, and this is a 1 D factor, this is a 2 D factor, and the 3 D factor, you can see there's the formations of this impurity band. So if you calculated the transmission coefficient for this the two-dimensional the conductors, you will see for the periodical boundary open boundary conditions. So the transmissions coefficient is a 1, and then you increase the concentration of the D factor, we observe a change from 1 to zeros. Here we just consider the component for the spin up. If we use the periodical boundary conditions, you will see there's no edge state for the small p, but it will change to another ones. We have a non-zero conductance near the transition point. So the conclusion is that if we can, the D factor can induce quantum phase transitions between the quantum spin Hall factors to the conventional insulators. So this is for we call some of the D factors is non-topologically the D factors. We have some other type of the D factors. We say the domain wall, such as magnetic flux or magnetic monopoles. So this for the 2 dimension, suppose we have magnetic flux surrounding the holes. So we simply change the P to introduce the vector potentials. So you will find this with magnetic flux, you see the energies will be changed. But however, if the mu, this is 1/2 the magnetic flux, you'll find there always one state, the energies is equal to zeros. The energies are independent of the radius. So very, very stable. So what happens for this equation, we just solve this problem analytically. You can find the equation for the radial part of the wave functions actually is exactly the equivalent to the equations for the one dimensions, from 3 dimensions to 1 dimensions, when the mu is equal to 1/2. So that's why this state is very stable. So here's another effect is if you have for 3 dimensions, if you have a magnetic flux through a hose. So you can have a very special property. For 2 dimensions, we can have this zero energy mode. And if you use this 2 zero energy mode, you'll find actually there is a 1-dimensional conductors. So this is for the another interesting problems. If what happens if we have the magnetic monopoles in the topological insulators. So fortunately, this problem can be solved exactly at for the total angular momentums is equal to zeros. So we can find the solutions. So actually for the radial part of this, the wave functions also is equivalent to the 1-dimensional equations. If you take the rho, it's very, very large. So we can consider a sphere with a radius r. So you see this actually is the same equations. So if MB greater than zeros, we find there is a zero energy mode near the surface. And also there are another zero energy mode around the monopoles. the monopoles. So we have the two equations. I mean, if the radius is large enough. If this the spheres become smaller and smaller, so degeneracy of this two state will be shifted. So it will be split into two parts. The one half near the magnetic monopoles, another half near the surface. So the energy gap between these two states is exponentially decays with a radius. So there is the questions. We know the magnetic monopoles in the action equation. There is a so-called the weighting effect. That means what the meaning is that if we have magnetic monopoles in an action mediums, they will induce the half the charge around the monopoles. So now we solve these problems exactly for the magnetic monopoles in topological insulators. We find a pairs of the zero energy mode. So what's the meanings of these double degeneracies? That's the charge near the magnetic monopoles actually is not the certain. It can change from the 0 to 1. Why? We say because in this system, due to the particle hole, the symmetries, the energy level is exactly at the E equal to 0. So at half filling, there is only the one electrons occupy the two states. At least from these exact solutions, it does not support this so-called the weighting effects in the topological insulators. So although you say, oh, the one half is also possible, but we have other possibilities. So this is so if you like, actually, you can also say what happens in the P wave, the superconductors. In the P wave, superconductors actually is also related to this so-called the modified Dirac equations. So if you have the Cooper pairings, you introduce the spinner, the spinners, then you can write the equation as a 2x2 matrix. Then from the so-called the Bogoliubov-Dejean equations, you can find that actually we got the same equations for the P wave, the superconductors. So this is one dimension. So this is 2 dimensions. Here, these magnetic chemical potentials play as a role as a energy gap. So you see, this is the same equations as topological insulators in 1 dimension. This is for the P plus IP. We have these ones. So the one interesting the solution is the so-called the Medrano formulas in these systems. So you see, this is in 1 dimension equations. We have the 2 zero energy mode. But because this is so-called particle hole symmetries, actually there is only the 1 state. So for these Medrano formulas, they're always non-locals. The state is separated at the 2 ends of the systems. So Medrano, the fermions in 1 dimension is non-locals. And for 2 dimension, we know the magnetic flux can induce the Medrano fermions. You see, we got the same equations as 1 dimensions. So that means for the Medrano fermions near the magnetic flux, it is also non-local. 1 half near the center, another half around the boundaries. So this is from the solutions of these equations. So actually, we can use these equations to describe the band topology for a lot of the systems. But this condition is that this dimensionless parameters should be greater than 0. If the m equal to 0, B equal to 0, that is marginals. But B is not equal to 0, it can be the topologically trivial or non-trivials. So for the non-topological insulators, you can induce a lot of the in-gap, the bound state. So, but for the topological impurities, so we have a so-called the zero energy mode, so vortex-induced zero energy state. So anyway, it seems that this equation is very useful to understanding all these topological phases we know. Okay, thank you very much.
Questions?
Yeah, I don't understand this equation. So what do you mean? It can be used to describe these topological things, but when it's applied to the classical case like hydrogen stuff, this term is automatically gone?
So this equation is it becomes valid when the system near the transition point. If the gap is not very large, we can always suppose, for examples, you can expand the Hamiltonians using Tanner series expansions. For examples, for this term, this actually is the gap between the two bands. So this is the first order, the correction. This is second order corrections. So for example, if the system has time reversal, the symmetries, so you see on the time reversals, beta remains unchanged, but the alpha changes minus signs. So that's why we have first terms, this is second term, this is third terms. So on time reversal, the symmetries, we can, if you use the Tanner series expansions, so actually you can have these equations. And also, topological insulator has a very special properties. So if there is no the energy crossings, so the topological property does not change. So sometimes maybe the band structure is quite different from this one, but near the transition point, we can always use these equations to describe the properties.
Any other questions? Yes, Shun-Qing.
There's a question. So, so for the one-dimension case, the symmetry case, if you consider the impurity, you have a bound state, and as you mentioned, if the impurity is infinite, if you have an infinite strength of the impurity, then actually you can treat the y as two independent y's.
Yeah,
then you
yeah.
have the two zero bound states. But actually, then you can consider this situation. One is for the infinite positive impurity. Another is the infinite attractive interaction impurity. The impurity with a repulsive interaction with infinite repulsive interaction. Another is the infinite attractive interaction. For the two cases, I guess the ground states of the two systems actually should be different. Then if you tune the strength from the impurity from the attractive infinite interaction to the repulsive infinite interaction, what happens? Maybe something interesting can happen.
You see these are solutions.
Yeah, exactly for this one.
If you from this
solution, if
we
zero changes from infinite attractive to infinite repulsive.
If you change the sign of this one, you see, you can also change the sign of the sigma x or sigma z. So the final result is that you simply change the signs of the eigenvalue for the energies. So that's for the repulsive, save the interaction attractive.
It doesn't maybe
just here. These are for the positive. This for the negative.
I guess for some case, if you
change the sign
for some value of V0, you may get the zero bound states.
Very clear from this equation.
May I have a question? May I have a question? Prof Shun.
Sorry.
So you always assume this particle hole symmetry in your your equation, is it?
Yeah.
So it's just a mathematical convenience, right?
Not simply mathematical convenience. For example, even for the topological superconductor proposed by the in that case, actually, if you make some the transformations, then, for example, the Dasama's models actually is equivalent to the two P-wave superconductors. So in the one P-wave superconductors is always topologically trivial. Another one is possibly non-trivial. So near the transition point, you can also use these equations.
Yeah. So that's okay. I mean, in the superconducting, in the superconducting case, I mean, particle hole symmetry is built in. But for example, in the topological insulator case, you can break the particle.
That is not a particle hole symmetries. For example, in this case, maybe some other symmetries. Yeah. Because we didn't write down the basis. It's just the Hamiltonians. Depends on the basis you choose. For example, in one dimension, that's a diamond model. It's just the AB lattice. AB lattice.
Any more questions? If we don't, we thank Professor Shen again.